Hello students, today we have gathered to discuss about the questions on relations and functions which are particularly of the advanced level, okay. Majorly among relations and functions, it's the functions portion which is utmost important, or basically I should say of a higher weightage than the relation section, and therefore the questions which we would be witnessing in this PPT today would majorly be consisting of questions or concepts about functions. So your concepts should be thoroughly clear about functions, all the types of functions, everything, all the characteristics of functions, everything should be clear with you before you start the problems discussion about functions. So let's deal with the first question. A function is given to you fx equals x plus 2 upon x minus 1, then. That's it. So the function is given to you. Depending upon what is the options demand, we will be proceeding with the solution. First option says is x equals f of y. So primarily in the first case, if I begin with the solution, you are given y equals x plus 2 upon x minus 1. That means y is given in terms of x. If you express x in terms of y, what do you get? So let's do that. Cross multiply. What you get? Yx minus y equals x plus 2. Club in the like terms. Yx minus x equals 2 plus y, which means x. Y minus 1 equals 2 plus y, which implies x is equals to 2 plus y upon y minus 1. If f of x is x plus 2 upon x minus 1, f of y is y plus 2 upon y minus 1. Y plus 2 upon y minus 1, which is f of y. That means yes, x is definitely equal to f of y. First option is very much correct. Next it is saying that if f of x is this, what is f of 1? Well, f of x is given to be this. What is f of 1, the question is demanding. Now, at 1, if you can very clearly see, this function is not defined, because when you plug in x equals 1, the denominator vanishes and therefore x plus 2 upon 0, right? That means 1 plus 2 upon 0, or I should say 3 upon 0 is an undefined term, it's not a real number. So f of 1 does not exist. In fact, it's only 1 which is creating a problem for f, and therefore only for x equals 1, f is not defined. Thus, domain of f is all the real numbers minus the term 1, since f of 1 is not a real number. If f of 1 is not a real number, definitely there is no question about f of 1 coming out to be 3. So second option is absolutely incorrect. There is no f of 1, so how will it be coming out to be 3? Third option says function increases with x for negative x's. So in order to talk about increasing or decreasing function, we basically move on to the derivative portion, which helps us combat the problem of increasing or decreasing nature of the function. So what we do, if we are given that fx is equal to x plus 2 upon x minus 1, you should be aware about the tools of differentiation, how to compute the derivative. The quotient rule basically will be applied over here, and then we are going to analyze the derivative, whether it is positive or negative for all the x's for which f is defined. So here I am interested in the derivative. This will be what? Second function. So I am saying this is my second function and this is my first function. How do you differentiate the quotient of two functions? Second function into differentiation of the first function. So differentiation of x plus 2 will be just 1 minus first function into differentiation of the second function, which is again just equal to 1 whole upon second function whole square. Fine, that's what is the formula. So here you have x minus 1 minus x minus 2 whole upon x minus 1 whole square. You can see this x, they get cancelled. What are you left with? You are left with minus 3 upon x minus 1 whole square. Now, x minus 1 whole square is always a non-negative term because x is not equal to 1. So, first of all it is defined, and for any x not equal to 1, x minus 1 whole square is non-negative. 3 is non-negative, and therefore 3 upon x minus 1 whole square is non-negative. But the moment minus sign is attached, minus of a non-negative term is negative. Fine. So, over here I have fx is coming out to be less than 0, not greater than 0 for every x belonging to the domain of f. For every x you plug in, minus 3 upon x minus 1 whole square is negative. This means what? F is a decreasing function for all x belonging to its domain. The option said f is increasing for negative x's, or basically x less than 1. But over here we are getting for all the x's, fx is decreasing. So it is not increasing for any x or over any portion of the domain, and that is why this is also wrong. If I talk about the fourth option, which is f is a rational function of x. Rational function means it's of the form gx upon hx, where gx and hx are polynomials and hx is not equal to 0 identically. Here you can see that fx is equals to gx upon hx, where gx is a polynomial, hx is a polynomial, and because the domain is this, therefore hx is not equal to 0. Fine. Therefore, yes, f is a rational function. Understood? That is how you combat the problem of this function. Basically, many a times when you're dealing with questions like these, the question itself doesn't give much of an information, but rather it is the options based on which you have to proceed with the solution, right? Like we did in this particular question. Okay? I hope the concepts are clear. Let's move on to the next question. It is saying which of the following functions is periodic? Fine. So, I want to know which functions are periodic functions. So, your concepts about periodic functions should be very clear before dealing with questions upon periodicity. The first question is, or the first option as I can say is, fx equals x minus greatest integer function of x, right? The moment I look at this definition, I have in my mind that yes, this function is nothing but the fractional part function, right? Isn't it? If I talk about the graph of the fractional part function, what can I say? If you remember, this is how it goes. And this continues. This is 0, this is 1, this is 2, this is 3, this is minus 1, and that's how it goes on. This is fx equals to fractional part of x. That means from x you remove the greatest integer function of x, you get the fractional part of x. You can see after every interval of length 1, or I should say over every interval of length 1, the design of this function is exactly the same. Fractional part function is very much a periodic function with period 1. So, fractional part of x is a periodic function. I don't need to answer about what is the period, but you should know that it is a periodic function with period or fundamental period, you can say 1. Fine. So, this is periodic. Yes, it's periodic. Fine. Then you have fx equals to sine 1 by x for x non-zero. Well, if I talk about the graph of sine 1 by x, beautifully crafted, this particular graph behaves in which manner? Now see, as x goes closer and closer to 0, 1 by x goes closer and closer to infinity, and so sine 1 by x keeps on oscillating between minus 1 and 1 rigorously, very rigorously. As you go closer and closer to 0, sine 1 by x keeps on increasing its oscillations just very close to 0 between minus 1 and 1, because its range is minus 1 and 1. and therefore there is no period. It just keeps on increasing its oscillations more and more and more and keeps on accumulating near this y-axis. So if this is your 1, this is your -1, I am saying that as you come closer and closer, the oscillations keep on increasing. This is how the graph of sine 1 by x looks like. It just keeps on becoming dense and dense and dense closer to the y-axis. And that is why this is not periodic. It does not repeat its behavior. Fine. Next, if I talk about x cos x, so basically B option happens to be wrong. If I talk about x cos x, this is very nice. The graphical representation of x cos x is nice. What does it say? Well, x cos x. Firstly, draw the graph of y equals x. Y equals minus x. And then you start drawing the graph of cos x. That is how it goes. Well, that's how it behaves. There is no period. So, x cos x is also not periodic. It is not repeating its design over a specific interval of time or after a specific interval of a certain length. That is why it is a non-periodic function. So, over here, even x cos x is not periodic. Which of the following functions is periodic? None of these above is also wrong, because yes, the fractional part of x was a periodic function. So, right now if you would have observed, basically the very idea of graph of a function helped me to come up with the answer to this question. Many times graphical approach is going to really help you to come up with the answer in a very short span of time, rather than proceeding with the conventional or traditional definitions, finding out that t for which f of x plus t is equal to f of x. All these things are going to take tons of time. I am not saying it's not possible to do with that approach, but definitely graphical approach is much more handy and less time consuming. Okay? Let's move to the third question. This is related to relations, and so let's try to combat this problem. It is saying if R1 and R2 are relations on the set of real numbers defined as this. So, you are given a relation R1, a relation R2 on the set of real numbers, means R1 is a subset of R cross R, where R I am saying is the collection of all reals. Similarly, R2 is the subset of R cross R. So, it is saying is R1 reflexive but R2 is not reflexive? I think not is missing. Then is R1 is not symmetric but R2 is symmetric. R1 is not transitive but R2 is transitive. R1 and R2 both are equivalence relations. The first option is going to say R1 is not reflexive but R2 is reflexive. So, basically it's talking about the reflexivity, symmetricity, transitivity of these two relations, on the basis of which we will be talking about or claiming them to be equivalence relations or not. Fine. So, let's begin checking the symmetricity, reflexivity and transitivity of R1 and R2. Firstly, starting with R1. What is R1? All those ordered pairs A comma B, where A is coming from the collection of all reals, B is coming from the collection of all reals, such that A is less than equal to B square. So, what is this relation trying to say? Any real number is related to another real number. First real number is related to second real number if and only if first real number is less than equal to the square of the second real number. Fine. If I talk about reflexivity, well, observe carefully. Is every number, can I say A is related to A? Is any real number related to itself by the relation R1? Is any real number less than equal to square of itself? Of course, no. 1 by 2 if you take to be equal to A, then 1 by 2 is not less than equal to 1 by 2 whole square, which is 1 by 4. right? Which implies 1 by 2 is not related to 1 by 2, which implies 1 by 2 comma 1 by 2 does not belong to the set R1, right? That is why R1 is not reflexive. Fine? So we have found two real numbers which are not, or basically one real number which is not related to itself under the relation R1. That is why my relation R1 is not reflexive, because reflexivity says A is related to A for every A belonging to the collection of all reals. But there is one A which is not related to itself, so the relation is not reflexive. If I talk about symmetricity, suppose I say that we need to check symmetricity. That means whenever A is related to B, it should imply B is related to A. Fine. Over here I am going to give you one A and one B specific real numbers. Suppose I say -1 is less than equal to 3 square, isn't it? You know -1 is less than equal to 3 square, which means -1 is related to 3 by the relation R1, or I can say -1 comma 3 belongs to R1. If my R1 is symmetric, 3 comma -1 should also belong to R1. But 3 comma -1 to belong to R1, 3 should be less than equal to -1 square, which means 3 should be less than equal to 1. Which is not true. This implies 3 comma -1 does not belong to R1, which implies R1 is not symmetric. Understood? That is what happens to be the case over here. Now, if this is not reflexive, not symmetric, let's see if it is transitive or not. Fine? So over here if we check transitivity, suppose I say, is this true? Is this true that 2 is less than equal to -3 whole square? Yes, 2 is less than equal to 9 definitely. This implies what? That 2 comma -3 belong to R1. Right? And can I say -3 is less than equal to 1 square? Of course, -3 is less than 1. This implies -3 comma 1 belongs to R1. So you have 2 comma -3 is in R1, -3 comma 1 is in R1. I have to show what 2 comma 1 is in R1 in order to show that R1 is transitive. So for 2 comma 1 to be in R1, 2 should be less than equal to 1 square, which is absolutely wrong. This implies 2 comma 1 does not belong to R1, which implies R1 is not transitive. Understood? Therefore, R1 is neither reflexive nor symmetric nor transitive. So forget about it being an equivalence relation. Fine? Once we are through with the behavior of the relation R1, whatever properties it is possessing, let's move on to check R2. Because the options are combined about the nature of R1 and R2. What is R2? All those ordered pairs A comma B such that A is less than equal to B. Fine? Now if I talk about reflexivity, is every real number less than or equal to itself? Of course, every real number is equal to itself. So A is less than equal to A for all A in the collection of all reals, which implies A comma A belongs to R2 for all A in the collection of all reals, which implies R2 is reflexive. Fine. If I talk about symmetric, is R2 symmetric or not? Suppose A is less than equal to B. Is it true that B is less than equal to A? Of course not. I can have 2 is less than equal to 3, but 3 is not less than or equal to 2. This implies 2, 3 is belonging to R2, but 3, 2 is not belonging to R2, which implies R2 is not symmetric. Fine. If I talk about transitivity, what do you think about transitivity? Well, let A be less than equal to B and B be less than equal to C. This obviously implies that A is less than equal to C, right? So therefore, if A, B belongs to R2 and B, C belong to R2, this is implying that A, C also belongs to R2 for all A, B, C in the collection of all reals. This implies R2 is transitive. Understood? Therefore, that is what is the conclusion we obtain about R2. R2 is reflexive, not symmetric but transitive. Let's move to the options. R1 is not reflexive. Yes, it's not reflexive, but R2 is reflexive. True. R1 is not symmetric, but R2 is symmetric. No, even R2 is not symmetric. Fine. R1 is not transitive, but R2 is transitive. Correct. R1 and R2 both are equivalence relations. Wrong. Because R1 is neither reflexive, nor symmetric, nor transitive, and R2 is not symmetric. That is why both of them are not equivalence relations. Understood? That is how you deal with this easy problem of this particular question related to relations. Just you needed to check the reflexivity, symmetricity and transitivity of these two relations and you would have been through with this question within no time. Let's see what is there waiting for us as the next question. Okay, so the fourth question again deals with functions. It says f is a function from closed interval 1, open infinity to closed interval 2, open infinity, which is given by such a formula x plus 1 by x. Then what is the inverse of x? Now already if the function is asking you for inverse, it is assuming that the function is 1, 1 and on 2. So you don't need to sit and check whether your function is injective and surjective or not. Just directly focus on finding f inverse by your basic algorithm, which you all would be aware about. So if I am given fx equals this, let's try and find out f inverse x. Fx is equals to x plus 1 by x, where f is a function given from 1, infinity to 2, infinity. Fine? So fx is this. Let fx be equal to y. So y is equal to x plus 1 by x, which implies what? Y is equals to x square plus 1 whole upon x, or I can put it x over here by cross multiplication. This means what? X square minus xy plus 1 equals 0. This means what? X square plus minus y into x plus 1 is 0. Nothing but a quadratic equation. I have to find x in terms of y, which I am going to claim as my f inverse. Right now I am given y in terms of x, I want x in terms of y. So let's find out x by the quadratic formula, because here before you is a quadratic equation. So this implies x is equals to minus b, which is just this, plus minus under root b square minus 4ac, right? B square minus 4 into 1 into 1, which is just 4. because A is the coefficient of x square and C is already given to be 1. So y plus minus under root y square minus 4 whole upon 2 into A is 1, so it's 2. So x is this. This means what you are getting, it is saying that f inverse y, that's what we do. If x is this, that means this is f inverse y or f inverse x, I can say. So over here, let me just first write what we have. X is equal to y plus under root y square minus 4 upon 2. And next you have x equals y minus under root y square minus 4 upon 2. Okay? Suppose we take this as my f inverse. Suppose I take this. So let f inverse x be equal to x minus under root x square minus 4 whole upon 2, where f inverse is a function from 2 comma infinity to 1 comma infinity, right? This means for all x coming from 2 comma infinity, f inverse x is going in 1 comma infinity. So this means here f inverse x is greater than equal to 1. If f inverse x is defined by this formula, then f inverse x is greater than equal to 1 for all x coming from 2 comma infinity. So if f inverse x is greater than equal to 1, then what? If this is my f inverse, it should be greater than equal to 1. Right? Let me right now just focus on it being strictly greater than 1. Okay? It has to be greater than equal to 1, but what if? Basically it has to be greater than 1 mostly, majorly. So f inverse x has to be greater than 1. This implies what? X minus under root x square minus 4 upon 2 has to be greater than 1. This implies for f inverse x to be greater than 1, x minus under root x square minus 4 has to be greater than 2. For f inverse x to be greater than 1, x minus 2 should be greater than x square minus 4 under root. For f inverse x to be greater than 1, x minus 2 whole square should be greater than x square minus 4. Proceed. X minus 2 whole square means x square plus 4 minus 4x should be greater than x square minus 4. X square gets cancelled, you get 8 should be greater than 4x, which implies x should be less than 2. For f inverse x to be greater than 1, x should be less than 2, but this particular f inverse x, if f inverse is defined like this, then f inverse x is coming out to be greater than 1 for x less than 2. But actually f inverse should be defined only for members greater than equal to 2. So, but x is greater than equal to 2, right? That means this f inverse is not satisfying my criteria. If f inverse is defined like this, it won't be able to deliver me f inverse x greater than equal to 1 for all x greater than equal to 2. What it is delivering is f inverse x will be greater than equal to 1 for all x less than equal to 2, but not greater than equal to 2, right? So majorly it is greater than 1, which it is becoming because of x strictly less than 2, which is not the case over here. That is why I am going to define my f inverse as not like this, but like this, which is x plus under root x square minus 4 whole upon 2. And why did I even decide to choose one among these two? Because inverse of a function is unique. It cannot come out to be two functions. So one of them had to be cancelled, and that is why I first always we are going to choose the one with a minus sign. Let's see if that is satisfying our conditions or not. Here it was failing to satisfy the given conditions, and that is why the next one happened to be our inverse. So over here if I go by the options, the first option you can see is standing to give you f inverse. Not the second, not the third, and not the fourth. Fine. So that is how you find your f inverse. Right now, as I initially also suggested, that you don't need to check the one-oneness and onto-ness of the function, because already you are being asked the inverse of this function. Okay? Not that difficult a question. Well, next, see what is the next question. Okay, so here again we are dealing with functions. Fx is given to be sine of pi by 6 sine of pi by 2 sine x for all x in the collection of all reals, and gx is given to be pi by 2 sine x for all x belonging in the collection of all reals. FOG of x, okay, so there's composition being talked about. FOG of x and GOF of x are being talked about. Then they are asking range of f, range of FOG, limit, and some more points. Let's try and first see what is the first option. It is talking about range of f. What is my f of x? F of x is sine of pi by 6 sine of pi by 2 sine x. Okay, nice function this is. Now over here, for all x in the collection of all reals is what it is trying to say. Fine. Now see, if x is in the collection of all reals, I know sine x is lying between -1, 1 closed interval. Sin x belongs to -1, 1 closed interval. If sin x is belonging to -1, 1, pi by 2 sin x will belong to what? -1 into pi by 2, that is minus pi by 2 to 1 into pi by 2, which is pi by 2. Now, if pi by 2 sin x is belonging here, what about sine of this? Whenever the angle is belonging in minus pi by 2, sine of these angles is ranging from -1 to 1 again, right? In fact, from here to -1, 1 sine function is injective and surjective. So this implies sine of pi by 2 sine x is belonging in -1, 1, right? Then you have pi by 6 of this. Pi by 6 of this of sine of pi by 2 sine x is belonging in minus pi by 6 to pi by 6, right? And sine of all of this is belonging where? Sine of pi by 6, sine of pi by 2, sine of x is belonging in sine of this interval, right? If this is belonging here, sine of this is belonging to sine of this. Now, sine of pi by 6 is 1 by 2, sine of minus pi by 6 is minus 1 by 2, and therefore, this happens to be the answer. So, for every x belonging in the collection of all reals, what is this? F of x. For every x belonging in the collection of all reals, f of x is belonging in -1 by 2, 1 by 2, which is the exact range of this function, and therefore, first option is very much correct. B, range of FOG. Okay, so for that we will have to first come up with what is FOG, and then we can talk about the range of FOG. So what is G? G is pi by 2 sine x. So what is FOG of x? It is f of g of x. So in place of x, put g of x. In place of this x, put g of x. Before that, let's copy the entire thing. Sine of pi by 6, sine of pi by 2, sine of gx, which is pi by 2 sine x. Fine, so there's a chain going on. So now, what is the range over here? This is also for all x belonging in the collection of all reals. Now let's discuss. For all x belonging to the collection of all reals, sin x is belonging in -1, 1 closed interval. Therefore, pi by 2 sine x will belong in minus pi by 2 closed interval. So, sine of this will be belonging to sine of minus pi by 2 closed interval, which is again minus 1 closed interval. Then pi by 2 of this will again belong to minus pi by 2 closed interval. After that, sine of this will be belonging to again sine of minus pi by 2 closed interval, which is minus 1 closed interval. Then pi by 6 of this will be belonging where? So, you had minus 1 closed interval, you are landing up at minus pi by 6 closed interval. And then sine of minus pi by 6 closed interval is just minus 1 by 2 closed interval. So, range of FOG is again minus 1 by 2 closed interval. Fine. And this is therefore the correct option. Fine. Let's talk about the third one, which is limit of fx upon gx. The option is that it is pi by 6. Let's see if this option is correct or not. So, we already have f of x with us. We need to evaluate limit of fx upon gx as x approaches 0. So, limit as x approaches 0, fx upon gx is what? Let's see. Limit as x approaches 0, fx is sine of pi by 6 sine of pi by 2 sine x upon gx, which is pi by 2 sine x. Here x is approaching to 0. See the smart manipulation which is almost natural to use over here, which I would be doing next is what? Limit x approaches 0, sine of pi by 6 sine of pi by 2 sine x. I am going to multiply and divide by pi by 6 sine of pi by 2 sine x. I have divided by it. Now I will be multiplying by it, which is pi by 6 sine of pi by 2 sine x. Already I have pi by 2 sine x in the denominator. Now see, if I make you recall about a standard limit, it says limit x approaches 0, sin x upon x is 1. That means whatever is the angle, if the same thing is in the denominator which is approaching to 0, then the limit is 1. Over here if you see, this is the angle, sine of something. This is the angle, the same thing is sitting in the denominator. That is why I did this manipulation. The only condition is that this thing should tend to 0, only then limit of this portion will be given by equal to 1, right? Now over here, see, if x is approaching to 0, sin x is going to approach to 0. If sin x is approaching to 0, pi by 2 sin x is going to approach to 0. If this angle is approaching to 0, sine of this angle is again going to approach to 0. Pi by 6 into 0 will again be 0. That means this angle or this denominator are approaching to 0 when x is approaching to 0, and that is why limit of just this portion is 1. Let's come over here. If you see carefully over here, just ignore this pi by 6 for a minute. See, you have sine of something. So this is that some angle which is there in the picture. The same angle is sitting in the denominator. Again the same logic, limit x tends to 0, sine of the angle upon the same thing. So sine of something upon the same thing. The only condition is that this something should tend to 0. So if x is approaching to 0, I know sin x is going to approach to 0, or sin x is going to approach to sine 0, which is 0. Therefore, pi by 2 of 0 will again be 0. That means yes, this is also approaching to 0. Therefore, sine of this upon the same thing, its limit is also going to be 1. So, pi by 6 is going to come out. This entire expression is also going to have limit 1. So, this will be 1 into pi by 6 into 1, which is pi by 6. That is what happens to be the case which you need to do. Fine. So what is this? Limit x approaches to 0, sine of pi by 6 sine of pi by 2 sine x whole upon pi by 6 sine of pi by 2 sine x multiplied by limit of, because limit of the product is product of the limits. This is what? Pi by 6. So this pi by 6 is going to come out. You're left with sine of pi by 2 sine x whole upon pi by 2 sine x. So the limit is 1 into pi by 6 into 1, which is pi by 6. And therefore, this is what happens to be your option, which is correct. Talking about the last option, it is saying there is some x such that GOF of x is 1. Let's see if there is some x for which GOF of x is 1 or not. Let's try to find that out. Okay, so G of f of x, which is G of f of x. What is G of x? G of x is pi by 2 sine x. So G of f of x is pi by 2 sine of f of x. This is equal to 1 for some x. Suppose it is equal to 1 for some x. This means what? That sine of f of x is equal to 2 upon pi. Right? This is equal to 2 upon pi, which is some 0.6 type of a number. If you replace pi by 3.14, this is what you're going to get, 0.62 something approximately. So this is what you're going to have. If for some x, GOF of x is 1, then sine of f of x will be 2 by pi. But f of x, we have seen the range is minus 1 by 2, 1 by 2. For all x in the collection of all reals, that was the first option. Fx belongs to this interval for all x. Now over here, if I want to see sine of fx belongs where, for that I will have to convert this thing into the angle part. Now minus 1 by 2, 1 by 2 is contained in minus pi by 6, pi by 6. Therefore, sine of fx will be belonging to sine of minus pi by 6 comma sine of pi by 6, which is again minus 1 by 2, 1 by 2. So sine of f of x will be belonging to sine of minus pi by 6, which is minus 1 by 2, to sine of pi by 6, which is 1 by 2. For all x in the collection of all reals. Now, for some x, if sine of fx is 2 by pi, that means 0.6, can this happen? For every x, sine of fx is less than equal to 0.5. So for some x, how can sine of fx be 0.6, right? Therefore, there does not exist any x such that sine of fx is 2 by pi, or there does not exist any x for which pi by 2 sine of fx is 1, or for which GOF of x is 1. There is no x. It is saying there is an x, but actually there is no x. Fine. This is what happens to be the correct option ticking related to this question. Fine. You have the solution with you. Take a little time to absorb whatever was done in this question in order to be able to mark the correct options, and then we will move on to the next question. Okay friends, let's now see what happens to be the case with the next question. Here again it's talking about relations with us. What is it saying? It is saying let A be this set, then show that the number of relations containing this ordered pair and this ordered pair which are reflexive and transitive but not symmetric are how many? Well, over here. Let's try and see how to combat this question. Okay, so I have A as the set. I have to show number of relations containing this and this ordered pair. Now if A is given to be this set, if I am saying relations on A, that means I want to find out subsets of A cross A. So first of all, any relation which is there on A is a subset of A cross A. What are the members which are there in A cross A? It's cardinality of A into cardinality of A, which is 3 into 3, that's 9. So A cross A contains 9 ordered pairs, out of which 2 ordered pairs are already given to you. I want to find out the relations which are reflexive, transitive but not symmetric, and they contain these 2 ordered pairs. So let's begin with this. Let's define a relation R1 on A. I want it to be reflexive and it should contain these 2 ordered pairs. So first of all, if A is 1, 2, 3, for reflexive I need 1, 1, 2, 2, 3, 3 inside my R1. Next, I also want these 2 ordered pairs to be there, 1, 2 and 2, 3. So this is the smallest reflexive relation which you have on A. But I don't want reflexive, I want reflexive plus transitive. So if 1, 2 is there, 2, 3 is there, for it to be transitive, 1, 3 should also be there, and so that is what I put, and this gives me the smallest reflexive plus transitive relation on A. But is this the only reflexive and transitive relation on A which is not symmetric? See, it is not symmetric. I have particularly made it not symmetric. 1, 2 is here, 2, 1 is not here. 2, 3 is here, 3, 2 is not here. 1, 3 is here, 3, 1 is not here. In fact, these are the only 3 ordered pairs which are remaining, because 6 ordered pairs have already been covered and A consists of 9 ordered pairs. We are left with 2, 1, 3, 2 and 3, 1. Now see, if I incorporate 2, 1 over here, 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3, if along with this I incorporate just 2, 1, only this, you can see again the relation is definitely reflexive. In fact, it is transitive as well. 2, 1, 1, 3 gives you 2, 3. Then you have 1, 2, 2, 1 gives you 1, 1. So every time transitivity is being satisfied. So this is one more reflexive plus transitive relation on A, which is not symmetric. Why? Because 2, 3 is here, 3, 2 is not here. Similarly, in R1, if I now adjoin 3, 2 over here, that is 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3 and 3, 2. Again, this will be reflexive, transitive but not symmetric, right? See, 3, 2, 2, 3, 3, 3, 1, 3, 3, 2, 1, 2. So it is satisfying transitivity and reflexivity. Similarly, in R4, if I say adjoin 3, 1 in R1, so it becomes what? 1, 2, 2, 3, 1, 3 and this time 3, 1. Again, it is reflexive, transitive but not symmetric. Now you are going to say, if these are your 4 relations which are reflexive, transitive and not symmetric, by plugging in 1, 1, 1 reflexive respectively in R1 we have obtained this. What if I plug in 2 at a time in R1? If you do that, you are going to end up forcing yourself to put the third one as well in order to ensure transitivity, which is going to give symmetricity as well. If you plug in 2, what I am trying to say is, if you put 2 ordered pairs out of these 3 at a time in R1, In order to ensure transitivity, you will be forced to plug in the third one also, which is going to make your relation to be equal to A itself, which itself is reflexive, symmetric and transitive. But I do not want symmetricity. That is why just plug in one of these three ordered pairs at a time to get these three distinct ordered pairs, and do not even try to plug in two ordered pairs at a time inside R1, because that is not going to give you what you want. And so that is it. These are your four relations on A which are reflexive, transitive but not symmetric, and therefore the number is 4 and not 7, not 9 and not 2. Okay, because specifically I did not want symmetricity to hold, so that was something I had to keep in mind cautiously. Okay, let's see what happens to be our next question. So here the seventh question is dealing with functions, and again invertible functions. It is saying if the function f from 1 comma infinity to 1 comma infinity is defined by this, then what is f inverse x? Again, we don't need to sit and ensure the injectivity and surjectivity of this function. We don't need to do all that. What we need to do is just find out f inverse x. So let's start. Fx is given to be 2 to the power x into x minus 1. What we do, we let y be equal to 2 to the power x into x minus 1. What you do, just take log to the base 2 both sides, because you already have 2 here, that is why. The benefit is that you are going to get x into x minus 1 into log 2 to the base 2, which is 1. So this is what you're going to have. This implies what? You have x square minus x minus log y to the base 2 to be equal to 0. If I have y in terms of x, I want to find x in terms of y, right? So what do we do? Again, quadratic formula. X equals minus b plus minus under root b square minus, so that is going to become plus 4ac whole upon 2a. So it's minus b plus minus under root b square minus, which is going to become plus 4 into a into c upon 2a. This means again what are you having with you is the same thing which we just dealt with before. X is coming out to be equal to minus 1 plus under root 1 plus 4 log y to the base 2 whole upon 2, and you have x is equals to minus 1 minus under root 1 plus 4 log y to the base 2 whole upon 2. So in order to eradicate 1, definitely only 1 can be the inverse function. In order to eradicate 1, we need to start with any one of them and see if there is a problem in 1. So if I start with this, so let f inverse x be equal to minus 1 minus under root 1 plus 4 log y to the base 2 whole upon 2. Here I will be just replacing this by x. Okay. So see, let's begin. If x is belonging to 1 comma infinity, because fx is from 1 comma infinity to 1 comma infinity, so f inverse is also from 1 comma infinity to 1 comma infinity. So if x is greater than equal to 1, you know that this is greater than equal to 0. Log 1 is 0, log is an increasing function, x is greater than equal to 1, log x is greater than equal to log 1, which is 0. 4 log x to the base 2 is greater than equal to 4 into 0, which is 0. 1 plus 4 log x should be greater than equal to 0 plus 1, which is 1. Then you have under root 1 plus 4 log x to the base 2 is greater than equal to under root 1, which is 1. Minus of this will be less than equal to minus 1. And what is ahead? Minus 1. Or basically I can say here it will be minus 1 or plus 1. It will be plus 1. Why? Because it's minus b, already minus is here, so this will be plus 1. So here you have, this is minus and therefore this is plus. So you get 1 minus under root 1 plus 4 log x to the base 2 is less than equal to 1 minus 1, which is 0. And therefore, this divided by 2 is less than equal to 0 divided by 2, which is 0. Right? That means this term is negative. Fine? That means f inverse x is less than equal to 0. But for all x belonging in 1 comma infinity, f inverse x should belong to 1 comma infinity, which is greater than equal to 1. So, but f inverse x has to be greater than equal to 1. But that's not the case. This implies this is not your f inverse x, this is your f inverse x. F inverse x is 1 plus under root 1 plus 4 log x to the base 2 whole upon 2, which is given as this 1 plus under root 1 plus 4 log x to the base 2 whole upon 2 and not this. Fine, that is what happens to be our case over here. Next, if we are going to proceed on to the next question, what is it that we are going to see? See, over here, as it is, the question also gave hint that log has to be used, and that is why we stepped into the usage of log. So once this question is done, let's see what happens to be the next question in the league. Okay, so a, b, c are given real numbers. You are given a function fx equals ax square plus bx plus c such that a plus b plus c is 3 and f of x plus y equals fx plus fy plus xy. For all xy in R, compute this summation. Let's begin. Fx is given to be ax square plus bx plus c. Then you have a plus b plus c is 3. Then you have f of x plus y equals fx plus fy plus xy. Fine. Let's see. We need to compute summation f of n varying from 1 to 10. So for that we need to have f of x clear picture with us. We do not have f of x. For f of x to know, you should know a, you should know b and you should know c. So the target is to compute a, b and c to get the clear picture of f and then get the clear picture of this summation. So how to do that? Firstly, what you do, let y be equal to 0. Here, this is true for every x and y. So let y be equal to 0. For that also it's true. You get f of x plus 0, which is f of x, equals f of x plus f of 0 plus 0 into x, which is 0. This implies f of 0 is f of x minus f of x, which is 0. So you get f of 0 is 0, but f of 0 is what? 0 plus 0 plus c. So f of 0 is c, so you have got the value of c. C is 0. Next, if you put y equals minus x, you can see to put, what are you going to get? F of x plus minus x, which is f of 0, is f of x plus f of minus x. Then you have put minus x in place of y, which gives you minus x square. Now, fx is what? Ax square plus bx plus 0, c is 0. So you get ax square plus bx plus 0. And what is f of minus x? Ax square minus bx. And then you have minus x square as f of 0, which is 0. So you get plus bx minus bx cancels, ax square plus ax square, 2ax square minus x square. That is what you have with you. So you have 2ax square minus x square equals 0. This is this. X square is always non-negative. So for x square into something to be 0, this thing has to be 0. 2a minus 1 is 0, which implies a is 1 by 2. Now you know a, you know c, you need to compute b. So let's use this relation. A plus b plus c is 3. So as a plus b plus c is 3, what is it that you have? 1 by 2 plus b plus 0 is 3, which implies b is 3 minus 1 by 2, which is 6 minus 1, 5 by 2. You know a, you know b, you know c. What is f of x? Ax square. A is 1 by 2. So 1 by 2x square plus bx plus c. So this is x square plus 5x by 2. If f of x is this, what is f of n? This is true for every real number. F of n is n square plus 5n by 2. And therefore, summation f of n going from 1 to 10 will be what? Summation n going from 1 to 10, 1 by 2 comes out, you have n square, plus 5 by 2 comes out, summation n going from 1 to 10, n. Sum of the squares of first 10 natural numbers is what? If I say find out the sum of the squares of first n natural numbers, it is n into n plus 1 into 2n plus 1 by 6. So here n is equal to 10. So you get 10 into 10 plus 1 into 2 into 10 plus 1 by 6 plus 5 by 2. This is nothing but sum of first 10 natural numbers. Sum of first n natural numbers is n into n plus 1 by 2. So sum of first 10 natural numbers is 10 into 10 plus 1 by 2, which eventually is going to give you 330 as the answer. Understood? That is how you first of all computed what is your f of x, and then you began computing this summation, which has come out to be 330. Okay? Pretty easy question. I won't say this is a difficult question, but the only thing it demanded was to be able to compute the value of ABC to get how the function looks like and then proceed with the question. Ninth question, okay, it is saying which of the relations is an equivalence relation? Well, A related to B, A if and only if A plus B is an even integer. Is this equivalence? Well, is this reflexive? Is A related to A? Let's see. If I say this is R1, suppose I say that's R1, this is R2, this is R3 and this is R4. So is R1 equivalence relation? Is it reflexive? Is A related to A for every integer A? For that I have to show A plus A is an even integer for every integer A. Well, A plus A is 2A, which is even for every integer A. Therefore, it is reflexive. What about symmetric? If A plus B is even, what about B plus A? Of course, A plus B is equal to B plus A. So, even B plus A is even. That means if A comma B is inside R1, B comma is also inside R1. That means it is symmetric. What about transitive? If A plus B is even, B plus C is even, then A plus C is what? So, if A is related to B, if A is related to B, B is related to C, is A related to C or not is what I have to see. So, for A plus C, if I want to see, I have A plus B is even, B plus C is even. What about A plus C? So, A plus B can be written as A plus B minus B plus C, right? Over here, you know, if you have two numbers which are giving you even answer, suppose I have say 2 plus, or I can say 1 plus 3 is even. 1 plus 3 is even. 3 plus what can give me even? If I say 3 plus 1 is giving me even, fine. 3 plus 2 is not going to give me even. 3 plus 3, 3 plus 4. So that means only even number, or basically I can say 1 or 3 or 5 can come over here to give me even. See, sum of 2 odd can give me even, or sum of 2 even can give me even. Fine. If over here I have both these as even, suppose A and B both are even, sum of 2 even is even. B and C both are even, sum of 2 even is even, then obviously A and C are even and therefore A plus C is even. If both are odd, A plus B is even, B plus C is even. If B and C also are odd, then A and C are also odd, therefore A plus C is also even. Fine, only then I can get even. That means in both the cases I am getting A plus C as even, and therefore this is an equivalence relation because it's transitive as well. Okay? Next, similarly you can see, is A minus B an even integer? This is reflexive, symmetric and transitive or not. Let's try and find this out. Obviously if I talk about R2, well, A is related to A because A minus A is 0 and 0 is even. If A is related to B, then is B related to A? If A is related to B, that means A minus B is an even integer. If A minus B is even, then B minus A can be written as this, minus of, it can be written as minus of A minus B. B minus A can be written as minus of A minus B. If A minus B is even, minus of A minus B is minus of this even, which is again even. Fine? And that is why this is symmetric as well. Similarly, if you talk about transitivity, if I am saying A minus B is even, B minus C is even, what about A minus C? A minus C can be written as A minus B plus B minus C. A minus B is even, B minus C is even, sum of 2 even is even, so even this is even. That means this is reflexive, symmetric, transitive, even this is an equivalence relation. Come to the third. A is less than B. We just discussed in some questions back that A is less than A. Well, even in this reflexivity only this is creating a problem. 2 is not less than 2, it is equal to 2. Or maybe if you want to check symmetricity, 2 is less than 3 but 3 is not less than 2. Therefore, this is not symmetric as well, and that is why it is not equivalence relation, which is the correct answer. Because I had to choose which relation is not equivalence. So this is not equivalence relation, so it's correct. And equality, it's very, very general that equality is definitely an equivalence relation. A is equal to A for all A equals B, B equals A. If A equals B, B equals C, then definitely A equals C. So this is a very, very easy equivalence relation, which is the equality sign. Fine. Let's see what happens to be our next question. Here we are given something about functions. Let f be a one-to-one function, okay? So f is given to me to be a one-to-one function. Domain is x, y, z, range is 1, 2, 3. So x, y, z is the domain, 1, 2, 3 is the range, and f is 1 to 1. Fine? It is given that exactly one of the following statements is true and the remaining 2 statements are false. So this is one statement, this is one statement, this is one statement. Then what is the inverse image of 1? 1 is sitting over here. What is the inverse image of 1? Suppose, okay, let's take the cases. If among these 3 statements, if this statement is true, fx equals 1. So let fx equals 1 be true. This implies rest of the 2 statements are false. This is false means fy is not equal to 1, so the false will be fy is equal to 1 is true. So fy will be equal to 1, and this is also false, that means f of z will be equal to 2. Just picture out. fx is 1, f is sending x to 1, f is sending y to 1, f is sending z to 2. This is not 1, 1, right? So case 1, according to case 1, I am getting if f of y is 1, then this particular case is giving me that f is not 1, 1. So this case is not true. This is not giving me the correct answer. Among these 3 statements, exactly 1 is true, rest 2 are false. So this cannot be true. Among these 3 statements, this cannot be true. That means these both of them cannot be false, because it is giving me the wrong conclusion and it is giving me f is not 1, 1. Among these 3, suppose this is true. In case 2, let's take f of y not equal to 1 is true. That means this and this are false. Then what do we get? Let's see. So first case cannot hold. Okay, so I have my f x, y, z, 1, 2, 3. Suppose, so case 2, suppose fy not equal to 1 is true. That means rest of the two statements are false. That means fx is not equal to 1 and fz is equal to 2. So what is it saying? It is saying y is not going to 1, x is not going to 1 and z is going to 2. So if y and x are not going to 1, that means 1 is not being obtained as the image for either x or y or z, because z is going to 2, y is not going to 1, x is not going to 1, right? If x is not going to 1, y is not going to 1, that means x and y, both of them are going to 3, or maybe y is going to 3, x is going to 2, or y is going to 2, x is going to 3. In any case, one-oneness is being hampered of the function f, because we are trying to map 3 elements to 2 elements in a 1-1 manner, which is not possible. And even in case 2, therefore, we are not getting the correct conclusion that f is 1-1 and therefore this situation is giving us correct answer. No, it's not doing that. And therefore we cannot have the second statement is true and the rest two are false. So the only case left is, what if the third statement is true and rest two are false? Let's see what happens then. So if I say that the third statement is true and the rest two are false, that means fz not equal to 2 is true. So what is false? Fx equals 1 is false, that means fx is not equal to 1. And this is false, that means fy is equal to 1. So can you arrange the members or the mapping in such a manner that all these three things are satisfied and f remains to be 1-1 also? Well, f of y is 1. Okay. Fx is not equal to 1 and fz is not equal to 2. That means z cannot be mapped to 2, so let me map z to 3. And x cannot be mapped to 1, so let me map x to 2. Because already f of y is 1. So now this mapping is satisfying this also, this also, this also, and even this. Therefore, case 3 is giving me the correct answer. Out of the 3 statements, it is this statement which should be true and these two should be false. And under this setup, I am getting y is going to 1 and only y is going to 1 because function is 1-1. Therefore, inverse image of 1 is y. And here you have inverse image of 1 is y. Understood? That is how you deal with questions coming from relations and functions. As I said, that functions portion is majorly more important than relations. Okay? I hope concepts were clear with you. I'll see you in some other lectures. Thank you. That's it for now.